you can probably get fairly easily the equation for the acceleration of the mass. If you think about this mass, this big block that falls, how many forces are acting on it? Well, the Earth is pulling downward. The string is pulling up. So this tension by vertical string, this tension by vertical string here is an upward force. So this particular force right here, force tension by vertical string, is in the Newton's second law equation for the mass. And so is the weight of the mg, capital Mg, the weight of the mass. So those two forces add up together to give you a net downward force. And that net downward force is the capital M times the acceleration of that mass m. I guess I could just kind of quickly, no, I'm not going to try to write all that in. I'm just going to write net force on that mass divided by the mass is the acceleration of m. That net force has the two pieces in it. The weight is bigger than the tension by the vertical string. Notice that the acceleration of that mass is related to the angular acceleration. Angular acceleration of the pulley, because the string doesn't slip, and it's related by the radius of the pulley. Because the string's not slipping, those two accelerations are related to each other. So we have a force, we have an equation for the mass, the motion of the mass, we have an equation for the rotational motion of the pulley, and all that's left is the rotational motion of this mass and the translational motion of that mass. So the cylinder is both rotating and translating, so I'm just going to write that way, even though I wrote it out earlier. This is the same equation. The acceleration of this cylinder, unfortunately the cylinder has the same mass, capital M, which I wish it didn't, or else I could just call it capital M. But I've already named the block M. The cylinder has an acceleration that's equal to the acceleration of the mass as long as the string isn't stretching. Then whenever that mass moves downward, the cylinder moves to the right. As long as that string isn't stretching, the acceleration of the cylinder and the mass are equal to each other. And so there's a Newton's second law equation for the translational acceleration of the mass. What forces act on the mass? Well, on the cylinder, the forces on the cylinder, there's only one. That string pulls it to the right. Sorry, that's not true. Let me draw this. Force, tension by horizontal string. Tension by the horizontal string which we already had an equation for that. There's a force upward by the table. force downward by the earth. And if this thing is going to roll without slipping, so the string pulls it to the right. It either slides to the right or there's friction. The thing that stops it from sliding to the right is a friction force, a static friction force to the left. So that's a friction force by the table on the cylinder to the left. In fact, that's what causes it to rotate. That's the only torque about the center of mass is due to that friction force. That friction force at the bottom causes it to rotate clockwise and to, in fact, accelerate clockwise. And so the sum of the forces acting on the cylinder are force of tension, horizontal string, we'll leave out the word tension. We'll leave out the word string. Minus the force of friction. Static friction is pulling the other way. So there's an equation for the translational motion. But this has two kinds of motion. It's rotating and translating. And so one final, what do we have? 1, 2, 3. One final equation, the alpha of the cylinder, the angular acceleration of the cylinder is the sum of the torques on the cylinder times the rotational inertia of the cylinder. The sum of the torques on the cylinder, well, as I said, the only thing causing this to rotate clockwise, all of these forces, except for friction, act through the center of mass. So don't produce a torque at all. Only the friction force produces a torque, and so the torque is just the friction force times that radius, which is 2r. Radius of the cylinder is 2r. So that's the torque that's on the cylinder that causes it to rotate. The angular rotation of the cylinder, if it rolls without slipping, alpha cylinder, well, let me do it in reverse. I did it this way. I said the acceleration of the vertical acceleration of this mass is related to the angular acceleration of the pulley. The angular acceleration of the cylinder times the radius of the cylinder is equal to the acceleration, the translational acceleration of the cylinder. And of course, the translational acceleration of the cylinder is the same as the translational acceleration of the mass. So you've connected up all of the motion of these things. These things all move simultaneously and they all move together. So if you knew one acceleration, you could find all the rest of them. And then the only question is to use these 4 equations to find out the things that you don't know. Okay, what don't you know? You don't know the acceleration, first of all. You don't know the whole acceleration. That's what it asks you to find. You don't know the tension in the vertical string. You don't know the tension in the horizontal string. And you don't know the force of friction. So there's one acceleration that you don't know, once you have that any of these accelerations, they're all connected to each other. They all move together. So if you know one of the accelerations, you can find any of the others. And so that's one unknown. And those three forces are three more unknowns. If you have four unknowns, you're going to need four independent equations. And that's what these four equations of motion give you. One of them is for the mass. One of them is for the cylinder. One of them is for the pulley, rotational. And one of them is for the rotation of the cylinder. So this is kind of as complicated a problem as you could have, at least in terms of how many pieces there are that are moving. It's still basically one-dimensional. It's even though this one's vertical and that one's horizontal, that's just because, I mean, this one only moves in one dimension and that one only moves in one dimension. And so it's basically a one-dimensional problem. Any questions on that kind of an issue? Yeah.
Will the acceleration be the same for every object if every object has the same mass?
The acceleration is going to be the same for this object and that object because they're connected by a string that's not moving, that doesn't stretch. So every time this thing moves a distance delta x, this one moves a distance delta x. Their motion, the motion of this one down and that one to the right are exactly, they match each other exactly. They have exactly the same acceleration because, not because the masses are the same, but because there's a string that ties them together. Yeah.
How much would this change if the pulley? So it's obvious, or at least I guess to me, that the middle of the string is exactly the height of the pulley, and so like what would change if you made it lower or?
So if the pulley looked like this, the string came down, and then it was attached to something like that.
Yeah.
Which maybe rolled on a surface like that, that would start to make it more than, I'm not sure how to draw that at this point. That would start to make it more than
four unknowns.
Well, yeah, it would, but it also wouldn't make this a two-dimensional problem because the motion of this thing to the right would depend on the horizontal component of this tension.
Okay.
And the vertical component of the tension would be related to the vertical forces. And suddenly I'd have to worry about vertical forces too, even though there's no acceleration vertically. But that would change things. It would make it computationally harder because it would turn this effectively one-dimensional problem into a kind of genuine two-dimensional problem, at least for that one object. Any other questions about what's going on here? The main idea, look at the motion, the various kinds of motion you've got, and apply one of these equations to figure every time you have a motion of some object that's either translational or rotational. Basically the plan for something like this.